Well, let's draw a Venn diagram containing two overlapping sets, A and B, and we usually represent those with circles or ovals or some kind of a shape like that. So this rectangle really represents the universal set, or when we're speaking about probabilities, we might say it's the sample space. It's a set of all possible outcomes. And then inside, we'll call that set A, and we'll call that set B. All right, so for any problem we're talking about, the area of the rectangle is going to be equal to 1. So in other words, we could also phrase that as the probability of S is equal to 1. Basically, S is all the possibilities, so the probability that one of those possibilities occurs, one of the elements in this rectangle is going to be 1. Something in this rectangle is always going to happen. Okay, and so A and B are two events that are subsets of the sample space S. Now, the area of the circle, or whatever shape we used for A, is the probability of A. Now, no, we're not going to take pi r squared or even use rulers or anything like that to find out the area of A, because we never, sometimes we don't know the probabilities of everything in the picture, so I usually use two equally sized, roughly speaking, circles. The probability of A may be way bigger than the probability of B, even though their areas look to be about the same. So typically we'll have numbers in here representing what those areas are. So we think of the area of the circle A as being the probability of A. And since it's inside this circle that has area 1, it's certainly going to be something between 0 and 1. The area of circle B, likewise, is the probability of B. The area of this region, which is what? That's A intersection B, this football-shaped region in the middle. Well, the area would be probability of A intersection B. And the area of any particular region is going to be the probability of an outcome occurring from that region. And before I leave this sheet, we could also say, we already know this, but it's worth putting the formulas in. If we're not thinking of it as areas, we can think of it as the number of elements in S, and we can think of the number of elements in A and the number of elements in B. And just using our definition of probability, this is equal to the number of elements in A over the number of elements in S. This would be the number of elements in B over the number of elements in S. And this one would be the number of elements in A intersection B, that football region, over the number of elements in S. All right, let's move on to our next problem. Number 5, we're starting off with a definition, and this is kind of the formal definition of conditional probability. If E and F are two events of a sample space, so that means they are just subsets of S, and S has equally likely outcomes like all of the problems that we've been working on. The conditional probability of E given F, we already know is denoted, the probability of E, vertical bar F. That vertical bar means given. So we're looking for the probability of E when we're told additional information that the event F absolutely 100% occurred. Well, this formula, this is defined as, in a Venn diagram, it could be the probability of E given F is the area of the region E intersect F over the area of F. All right, so let's come up with two other ways of writing that. This one is going to use the number of elements in event, so the little n. Well, I'm going to say the number of elements in E intersection F over the number of elements in F. That's the formula you should memorize. That's one of the formulas you should memorize. Very similar to that is a formula using probabilities. You can replace that little n with capital P for the probability. So basically that tells you that the number of elements in this set up here, the proportion of the number of elements in this set versus this set is the same as the probability from this set and this set. So the kind of the ratios are the same. All right, now we're going to draw a Venn diagram, and inside the Venn diagram, in each region, we're going to write the correct number of elements that belongs in each region. So here we go. Here's the Venn diagram. That's the entire universe, or the entire sample space, if you will. And I'm going to make a note out here that the number of elements in the sample space is 50. So how many elements are going to be inside this rectangle? 50. And now we'll draw the two overlapping circles, capital A and capital B. And yes, I realize those aren't very good circles, but they don't need to be. All right, so we've taken care of that. We've written this, that we know the rectangle has 50 elements in it. The number of elements in the set A is 25. But that number 25 is not going to go anywhere in this diagram other than this. It's not part of the Venn diagram, but I frequently will put in parentheses the number 25 next to A because I need to have a total of 25 in this circle. I'm going to put a number here and a number here, and they have to add up to 25. Likewise, with B, this is really not part of the Venn diagram either, but I put it there to remind myself as a hint that this circle, the number of items in this circle have to add up to 18. So it's going to be the number of items in this region and the number of items in this region. So that leaves us with one left, and that's what we're going to start with. We always start with the region that has the most overlap. This region is the overlap of A and B, the intersection of A and B. So this football region, I can directly put the number 10 in there because it says that the number of elements in the intersection is 10. So this football region, which is the intersection, I'm just making it known that it has 10 elements in it. From there, we work backwards. What goes here now? The entire circle adds up to 25, but I've got 10 already in this circle, so this is going to be a 15. Now I see that the circle adds up to 25. This circle has to have 18 elements in it, but I've already got 10. So that's going to be 8 there. Are we done labeling them? Not quite. We have one other region, this outside region. How many goes out here? And don't say 50. 50 is the entire rectangle, the entire universe. So let's see what these three numbers add up. We've already got 15, 25. We already have 33 taken care of. 15 plus 10 plus 8 is 33. So 50 minus 33 is 17. 17 goes out here. Now we have 50 elements displayed in this Venn diagram. And it says find the relevant probabilities. We could do, I don't know if I'll do all of them because there are a whole bunch of them. But let's start, maybe I'll go to I'll start up here. What is the probability of event A? Well, by definition, it's the number of elements in A over the number of elements in S. How many elements are in A in the entire circle? It's 25. We were already told up here. Number of elements in A is 25. Number of elements in S is 50. So we could reduce that if we wanted to 1/2. All right, probability of B. The probability of B is the number of elements in B over the number of elements in S. So the denominator is 50 again. Number of elements in B was 18. And that can be reduced. Since I reduced the other one, I'll go ahead and reduce this to 9 over 25. But I actually like to leave them unreduced, which is fine for you to do as well on a homework or a test, making it obvious that they have the same denominator. There's 50 possibilities and 50 elements in the sample space, so most of these probabilities before reducing will have 50 as the denominator. Probability of A intersection B. That's the number of elements in A intersection B over the number of elements in S. That happens to be 10. We've got that here, and we've got it in the diagram right here. 10 over 50, which reduces to 1 over 5. What else could we do? The probability of A union B. Well, remember what A union B is. It's this whole figure 8. How many elements are inside this figure 8? 15, 10, and 8, which would be 15, 25, 33 over 50. Another way we could have done it rather than adding these three numbers up is that I know this box, the Venn diagram, contains 50. If I would have taken 50 minus the 17, it would have given me this number, the sum of those three, which is 33. All right, since we're doing conditional probabilities, let's do some more examples here. What is the probability of A given B? Well, by our definition up here, we'll use this one since we're dealing with numbers and not probabilities inside the Venn diagram. It's going to be the number of elements in A intersection B over the number of elements in B. And that's really simple to see. What's the probability of A given B occurred? If B occurred, then we're in this circle right here. That's kind of our whole universe right now. And how many possibilities are there in this circle? 18. And how many of them are in the circle A? Well, not this 8, but these 10 are. So this is going to be 10 over 18. And you can see the number of elements in A intersect B is 10. The number of elements in the circle B is 18. 10 plus 8. Let's go the other direction. Let's do the probability of B given A. All right, well, that's the number of elements in B intersect A, which notice that's exactly the same numerator as this is, because B intersect A is the same as A intersect B. They both represent this football region, the intersection. Over, though, the denominator is going to be the number of elements in A. So the probability that B occurred, the probability that we're in the B circle, given that the circle A occurred, the event A occurred, this occurred, so we have 25 possible outcomes. How many of the possible outcomes in this circle live in the B circle? Those 10. The 10 are in both circles. So this is going to be 10 over the number of elements in the circle A, which is 25. All right, let's see, is there anything else we could do? I could certainly make up more, and maybe I will. Let's do a probability of B given A complement. All right, so by the definition, that's the number of elements in B intersect A complement. over the number of elements in A complement. So if we know how to count, we're done with it. We'll be done with this. Let's see. How many elements are, let's do the denominator first. How many elements are in A complement? Well, we've got 25 elements in A, right? So the number of elements in A complement would be this number and this number, 25 also. Or you could have said, well, I have 50 total, and 25 of them are in A. So the other 25 are in A complement. So 25. And I probably should have changed those numbers because it's not normal that this 25 will be the same as this 25. But then since there are 50 elements total, the number of elements in A is 25. If you're not in A, that means you're one of the other 25. Okay, so how many elements are there in B intersected A complement? Do you remember what B intersect A complement is? It means you're in the circle B and not in A. So that means you're in the circle B and not in A means you must be in this region right here. So how many elements are in that region? Just 8. 8 over 25. And since I did that one, maybe I'll come over here and do the probability of A given B complement. Well, that's the probability of A intersect B complement over the probability of B complement. I'm sorry, I wrote P's instead of N's. That's absolutely correct because of this formula, but it's easier for us now to use the N formula. So I'm going to replace this P with an N, lowercase n for the number, like that. All right, so I'll do it the same way I did last time. What's the denominator? How many elements are in B complement? Well, first we say how many elements are in B is one way of doing it. And I see 18 in B. So what's 50 minus 18? That'd be 32. Basically, if you're not in the circle B, you're either in this region that has 15 or the region that has 17. And that adds up to, those two numbers add up to 32. And then how many elements are in, oops, that was the denominator, that's 32. I'm going to change the numerator. The numerator is the number of elements in A intersect B complement, which means you're in A and not B. So here's A. But if you're not in B, we got to get rid of this 10. So if you're in A and not B, the intersection of A and B complement, you're in this region of 15. So that's going to be 15, let me write it again, equals 15 over 32. And there are other, I could come up with more, but I think that gives us a good feel for how to get all the probabilities from a Venn diagram where all of the regions in the Venn diagram have the number of elements in the set.